formula of oxalic acid is COOH, COOH, right? No, not really. Actually, the formula is dot 2H2O. If in any examination you want to calculate the molarity or normality, then you need the molar mass of this oxalic acid. Then if you take only this part, your answer will not be correct. Okay, so you have to take both this. So if you add both the things, COOH plus 2H plus 2H2O, the molar mass comes 126. This part 90, carbon 12 plus 12, then 4 oxygen means 32 into 2, then 1 plus 1 2. So total 90, and 2 water means 18 into 2 36. So total 126. It will be molar mass for oxalic acid. Now to prepare oxalic acid, what you have to do? Suppose you want to make m by 20 or m by 10 oxalic acid. That means m by 10 means actually 1 by 10 molar. So 1 by 10 molar oxalic acid. 1 by 10 molar means actually if we define 1 molar, that means 1000 ml solution you have to make. The volume of the solution should be 1000 ml, and here if you add 1 mole, not add, total solution should be 1000 ml, and in this 1000 ml solution if you have 1 mole oxalic acid, then the solution will be called simply 1 molar oxalic acid, right? So suppose you have to make 250 ml. Suppose you have to make 250 ml oxalic acid of m by 10 concentration. So in this line, in this equation, if we modify a bit, then it will be 1 mole oxalic acid means we have found the molar mass here. That means 126 gram oxalic acid. Let's modify it a bit. 1000 ml volume, 1 molar concentration. To make 1000 ml volume of 1 molar concentration of oxalic acid, we have to add 126 gram oxalic acid. Then 250 ml m by 10, that means 0.1 molar. M by 10 means 1 by 10 molar, that means 0.1, right? So what you have to add? This you have to calculate. What will be the answer? Then 126, 1000 ml 126, then 250 ml means 126 by 4, isn't it? Because 1/4 of 1000 is 250, into 1 molar means 126, then 0.1 molar means into 0.1. So 126 by 4, that means 4 into 3, 12, 4 into 1, 4, 2, 6, 20, 31.5 into 0.1, that means 3.15 gram. So what you have to do, in the weighing machine, you have to weight 3.15 gram oxalic acid. Now one very important thing, this oxalic acid is primary standard. Primary standard means its concentration is fixed. That means you have to prepare it by a primary standard method. That means you have to make the solution in this volumetric flask, not in conical, not in beaker. Okay, so this is the standard protocol. You have to make the solution in volumetric flask. So you have to take volumetric flask of 250 ml, and volumetric flask comes with a cap, like a cap. In 250 ml volumetric flask, that should be cleaned enough. So you have to add this 3.15 gram first. 3.15 gram solid. You will get it solid, in solid form, crystalline form. Then you have to add it in that volumetric flask. After that, you have to add distilled water And when adding the distilled water, take care of those oxalic acid. When you are pouring the solid oxalic acid, then some oxalic acid may be in the inner chamber of this flask itself. So what you have to do, you have to add water in such a way that all these oxalic acid dissolve. So after that, you have to lock the cap and you have to shake it very well. And after that, your 250 ml 0.1 molar oxalic acid solution is ready. Now the problem arises when they tell you or they assign you a work to prepare 250 ml 1 normal. Now it's your homework and it's pretty easy. In normality, what is the problem here? You have to know the molarity and normality relation here. And you know, molarity and normality are interchanged by a factor called n factor. And if you know the n factor for oxalic acid, then your task is pretty easy. Suppose one normal is here, and if you can convert it to something x molar, suppose, if you know one normal means that much molar, then your task is pretty same like this, isn't it? So I am telling you n factor, and you can try it yourself and you can verify it by Google by searching this type of question, that one normal oxalic acid means how many molar oxalic acid. You will get clarified over there. Here n factor is, for acids, the n factor is its basicity. That means how much proton, how many number of protons it may donate. Here, there are 2 protons, so here n factor is 2. Now the last part of this lecture is about this 2 proton. As we know, the basicity of this oxalic acid is 2. That means it can donate 2 proton. Then obviously we can predict that the rate of donation of 2 proton is not similar. Suppose this proton donation is the equilibrium constant, k equilibrium, for donation of this proton is 10. For donation of this proton will not be 10. So when first proton is donated, second proton donation equilibrium constant value will not be similar. Now if I talk about pKa, we know equilibrium constant is related to pKa. If pKa of first proton, suppose HA and HB, if for first proton the pKa is 1.27, is the exact value, known value 1.27. For the second proton, it's 4.28. What does that mean? We know from pKa we can calculate equilibrium constant. pKa means minus log Ka. Ka means actually equilibrium constant. For acid it's called Ka, for base it's called Kb. That's nothing but equilibrium constant. And from here, if you want to calculate Ka or equilibrium constant, then it will be 10 to the power minus pKa, isn't it? So for HA, equilibrium constant is 10 to the power minus 1.27. For HB, it's 10 to the power minus 4.28. That means this is lower. And how much? Almost it's 1,000 times slower, isn't it? Removal of HB proton is 1,000 times slower than HA. Have you understood it with the numerical value? You calculate the HA value from here with your calculator, and you calculate the HB for equilibrium constant value from here. And if you take a ratio, then you will get it almost 1,000 times, 1,000 times slower, 1,000 times lower value. So that means HB proton removal is very, very slow than HA, almost 1,000 times slower. Why is this so? That's a very, very important question. Actually, the answer is when there is C double bond O, C double bond O, OH. When first proton will be removed, it will be O minus, isn't it? And when it will be O minus, it will more prone to hydrogen bonding, because negative charge and hydrogen bonding. Initially, it was lone pair with hydrogen, isn't it? So this is 5-member stable 5-member chelate complex ring is formed. Not complex, chelate ring is formed. So because of this stabilization, this proton is now stable here. It will not prone to donation very well as compared to the first proton. That's why the second proton removal is very slow. I hope you have understood it. Thank you.